Hi everyone, welcome to the IEEE PS Big Data webinar. And today we are honored to have Professor Sukumar Brahma from Clemson University. The topic today is power system protection and big data challenges and opportunities. As a protection guy, I'm also very interested in this topic because as we know, the development of protective relays has transitioned from mechanical types to semiconductor-based relays because we have, by that time, accumulated enough knowledge on mechanical engineering and the semiconductor industry. Then, with the advancement of satellite technology, we have PMUs. Now, the question is, will AI or machine learning be the next generation relays, will be the game changer? And today, I want to hear some of the answer from Professor Brahma. So today, the talk will be around 75 minutes long with Q&A. If you have any questions, please feel free to send me the questions through the chat box. And now I'll give the speaker to Professor Wang, who will give us a brief introduction to Professor Brahma.
So for your information, Chosa and I are looking for the leaders in the protection domain, especially the one who are connecting technology to data to protection. So we are very lucky today to have Professor Brahma here to talk about his vision and his idea. So Dr. Brahma received his bachelor from Gujarat University and a master degree from IIT Bombay. And the PhD is from Clemson University, all from electrical engineering. So he also is with a title in Clemson University, Median Energy Distinguished Professor in the Power Engineering and the Director of Clemson University Electrical Power Research Association. So if I pronounce correctly, this is Sukumar. Before joining Clemson, he was William Christine Indo's chair professor at New Mexico State University. He has chaired the IEEE Educational Committee, which has a great impact over here, and we want to collaborate. He also chaired the Distribution System Analysis subcommittee, which is also very important for AI in power because transmission grid is very nice and very good, well formulated. He's a member of the PSRCC. He has been an editor and guest editor-in-chief for IEEE transactions on power delivery. His research interests span across diversified areas of electrical engineering and computer science, and to have cutting-edge approaches to emerging problems like what we are talking in this webinar series. Finally, Dr. Brahma is a distinguished lecturer and a fellow of IEEE, and I look forward to this great talk today. Professor Brahma, thank you.
Thank you, Yang, and welcome everyone to this talk. Well, hopefully we will have a good discussion. I think that's probably what is needed because there is a lot of questions on both sides. The protection people are looking for, what they can do to improve their system, and the data analysis people are always trying to get into, other domains where they can make an impact. So, so if you want to start this, I'll tell you a quick story where I think it was about 2003 when I had just graduated, done my work in protection and started doing protection. A colleague of mine who works in data science and AI, even then he worked in that area, said, you know what, all these things that you're doing in the next 10, 15 years, that will be done by machine learning. And I said, well, we'll see. So now it's been, almost 17, 18 years, and there has not been a single relay that has a machine learning feature in it. And talking to quite a few industry people that, you know, I regularly interact with, they are not thinking a lot about that as of now. At the same time, so that is one side of the story. The second side of the story is that, as Yang mentioned, I go to the Power System Relaying Committee meetings a lot, and almost every meeting I attend. And recently, there has been a working group on applications of AI in protection. So that is being chaired by Dr. Yi Hu, and I'm a part of that. So it's not, you know, it's not all bad. It's people, as I said, have started looking at, you know, how we can use AI to do that. One of the projects that I'm working on from DOE with Sandia National Lab, the Sandia National Lab folks are doing a lot of extensive application of, so they're trying to use machine learning for the protection applications where the legacy protection is failing in the distribution systems and microgrids. So this is, you know, that's why this is important that we look at, you know, we basically need to look at what the protection is, right? What protection is. It's been there for decades and decades. It's been fine-tuned, and as it was mentioned, we graduated from electromechanical relays to solid-state relays, and now we have all numerical relays. So what we'll do is first we'll have an overview of protection, you know, how it is done, and what are the metrics for reliability, and so on and so forth. And then use of AI in protection. So where it can, so basically first I'll probably talk more about pitfalls, because I'm basing my observations on the papers that have been published until now on you know, use of AI in protection. I've reviewed a few. So I'll talk about that. Based on that, I'll make some observations, and then we'll see what actually should be the way to go forward. And then while I was at New Mexico State, we did actually end up using machine learning for about 5 years on an NSF project. And I'll talk about, basically that project will display everything that I mentioned before. What are the challenges? How to get around that? So that is the plan. And then, as I said, you know, questions and answers would probably be great at the end. So here is essentially what we do, okay? These are the events that you see. I think this will help me if I have a laser pointer. So these are the events. There are lightnings, flashovers, you know, woods, I mean, the trees touching the wires, some pretty, you know, brave animals trying to rest on the wires. All these things we want to capture as a fault, right? So as you can imagine, all these events are so different than each other that they will give you different signatures. They are not giving, you know, they are not going to look alike. So, so that is why. What are those? So, what are the different things that we'll see? We'll see, you know, the different forms.
Oh, Professor Brahma, you are muted. Hi, Professor Sukumar, Brahma. So what I see is I cannot hear you. Chosa, can you hear?
Yeah, now.
Oh,
so I
okay,
don't know
perfect.
how I got muted.
Okay.
Yeah.
So how long have I been muted?
No problem. 10 minutes. not 10 minutes. 10 seconds. Yeah, it's all
okay.
good.
All right. So I've not been talking to the ether for a long time.
Right. And the pictures are very meaningful, so we enjoy them.
Okay, cool. So yeah, this is, I use these to get the students interested. So these are some of my slides in the power system analysis course and when I do fault analysis. So just basically, letting them know that there'll be very different signatures for different types of fault, but why we heavily depend on the phasers here are because the phasers have some kind of consistency across all these different types of faults, not only the reason for the fault, but the type of fault, line to line, line to line to line, line to ground, all these faults, all these other elements that you see here, the harmonics, the transient, the decaying DC offset, all these vary a lot. And it is very hard to use those signatures consistently for detecting and isolating fault. But the fundamental values, the phasers of V and I, have a more or less consistent behavior across all reasons of faults or types of faults. So this is basically what we do. Now, coming to the distribution system, because as you guys are all working on a lot on distribution systems and grid edge. In distribution system, this is what happens. So this is a protective device, okay, which constantly senses the state of the system, which is in this case is just voltage and current, okay. It is converted to phasers. Now we talk about numerical relays. It's converted to phasers, and these are it could be frequency as well, okay? So, and these are then compared with threshold values. And if it is greater than a certain, so if current is greater than a certain value, or voltage is less than a certain value, then it is declared that that's a fault. Now that X max or X min, these are the thresholds that we set, and we'll talk about that. If it's not detected, it just goes on in the loop. Now, if it is detected, it needs sometimes to wait. Depends whether that is a primary zone. That means this protection is in charge of its own zone, or is it backing up something else, right? So based on that, there's a wait time, right? And then the action is taken, which means the relay operates, the breaker opens, or the fuse blows, and then there's an outage and a restoration. So this is all real online process. But these, how do you decide these thresholds? Well, the thresholds are decided for distribution systems. They're decided by offline short circuit analysis, or fault analysis, as we call it, where we have system data. We create models out of that. Many of you are familiar with the most common model we use is a bus impedance matrix, right? And then you do fault analysis. That means you figure out, every type of fault at every bus in the distribution system, what is the fault current going to be? Based on that, you get an estimate of what constitutes fault and what doesn't constitute fault. So overload, for example, is not fault, but anything more than 2 times the rated current is a fault, something like that. And then the protection methodology, which is over current, under voltage, or frequency, or under frequency, depending on where you are implementing the protection, these are decided. And then those are the also the wait time is decided from here, and the thresholds are decided from here. For distribution systems, you have some more time because it's low voltage, but still about 10 cycles, up to 10 cycles. Some usually quicker is okay. For transmission, it's 3 to 5 cycles because, so here it is decided based on the stability of the system. Here it is decided based on the actual damage to the equipment. Those are the criteria to select the time, allowable time for the fault to clear. Okay, now here's the thing, North American distribution systems, we use extensively fuses and reclosers. So, and we'll talk about that later. So since we're talking pattern creation and you know, classification, is it really new to us? Well, as we saw, the relay uses a feature or a combination of feature and a rule-based classifier. What are the features? It's typically a frequency domain transformation, okay? Because you measure time domain data, voltage and current, and then you get current, voltage, frequency, power, impedance, harmonic content, you know, high frequency content. All this comes as a frequency transform of the time domain data. So these are our features, and then our protection logic is based on a combination of features, which is a pattern, basically, right? For example, voltage monitored over current, or fault detector monitored distance. So that's a pattern, right? What is our classifier? It has two classes, fault and no fault, right? And what is the separation plane? That is the threshold value that we talked about, right? And the threshold value based on system analytics, physics and physics-based models, because those are the models that are used for system analytics, and most importantly, experience. So the protection engineers, so one of the first books on protection is titled Art and Science of Protection. So the protection engineers they're a little cocky about it, that they're just not scientists or engineers, they are artists also, because there's this experience that tunes everything they do. They don't apply the same method in the same way across different circuits or different systems. So that's what it is. So it's there just to, you know, so it's not new, it's just not learning based. And then you have zones. This is a humongous system, right? Every point in the system, every location needs to be covered by some protection. So we have generators, we have bus bars, we have lines, and then all other equipment, motors, loads, capacitor banks, reactor banks. They all have their own protection, which is considered the primary protection. And as you can see, the zones are actually overlapping. So that means that there is no place in the system that is not protected. Yeah, in this, if there's a fault here, two protections will operate, but that's okay compared to nothing operating. So that's how it's done. Now, in each zone is protected by its own protection, primary, and always has a backup in case it doesn't operate. So this is what we need to understand, is that it's a coordinated system, okay? If you, and most of the papers try to do that, if you try to replace any one isolated element or one zone with AI-based or machine learning-based methods, you are not taking into consideration this whole coordinated protection system. And that's where you can run into problems. Okay, quickly, what are the metrics for protection? Reliability. Well, reliability has two aspects: dependability, which means if there is a fault, the device must operate. So number of correct trips divided by the faults in the system. Security, so there is another part of it, okay? It should not operate incorrectly for fault. So if the fault is in the other zone, it should not operate. It should operate only for the faults in its own zone. Plus, if there is no fault, it should obviously not operate, right? That's the security part of it. And if this happens, then it is called a misoperation, okay? The misoperations are, and we'll talk more about misoperations, because these misoperations are the only thing, after all these years of protection, misoperations are the only events which still cannot be detected in real time. So if there is a fault, yeah, the system is going to, something is going to operate. If it doesn't operate, something else is going to operate. That is really very, very well taken care of. But if it operates without any reason, for incorrect settings, for example, some problem with the relay itself, Virginia Tech guys in the 90s came up with something called a hidden fault, which you don't know, but suddenly it manifests itself. That is still, so remember this, okay? This has still no protective system is able to detect misoperations. Okay, selectivity. So now look at how much redundancy is built in. So for example, this is, if you take as a simplified distribution feeder with section 1 and section 2 here, right? And if there is a relay system, if it's fused, then it's just a fuse. But if it's a relay system, you have phase A, phase B, and phase C relays, and you have a ground relay, which is right here. So for any type of fault, say for example, take A to B fault. If it's A to B fault, there are at least 2 relays that will see and operate for that fault. So if one relay has a problem, the second still operates, right? If it's a phase to ground, then phase relay and ground relay are the 2 relays that will operate. So there is a redundancy built in right here at the local level. Now, suppose in this case, the relay would trip the breaker. Suppose the breaker doesn't operate. Or suppose the current transformer, the voltage transformer, something wrong with them, and this scheme fails. Then this fault is also seen by this relay here, okay? And that's why the waiting time. If it waits for this device to operate. If it doesn't operate, this will operate. Now here is a 100% redundancy, right? Different relays, different CTs, different VTs, different breakers. So that is why, so just observe the urgency to clear the fault. This is how it has been set. And that is why, it's very, very unlikely that a fault will just go on and something is going to operate. So this interdependency again is critical, okay? And if most of the papers that I see will do something here, but then say, okay, I am doing better than the legacy scheme for here, but what about backup? There's no backup there. So that is something that I consistently see in the papers that are published on this topic. Speed, of course, speed is important. And as I said, 100 to 500 millisecond for distribution system is not uncommon. 50 millisecond is typical for transmission, because transmission it's based on critical clearing time, which is stability dictated. Here it's dictated by the damage curve of the equipment. And then backup obviously compromises the speed. So these are the metrics for evaluating how good or bad your protection scheme is. This is our distribution system. Most parts of the US has fuses and reclosers, okay? The fuses coordinate with each other, and then the fuse coordinates with the recloser. So this is because it's cheap and simple to implement, and because all distribution systems until now were fed by just one source, which is substation source. So any fault that happens here, right, anywhere in the system is going to have fault current flowing only in one direction. So that is the assumption, and the system is radial. There are no loops involved. So these are the assumption on which all protection systems were built in the US and still are built. And that, of course, as you know, is changing, and we'll talk a little bit about that. And then again, what is the fuse and the recloser? Well, what happens is about 80% or more faults are temporary. And this is another aspect that I've never seen the machine learning based methods address, that what happens if the fault is temporary. So if more than 80% of the faults are temporary, do you want to really blow the fuse or operate a relay? Obviously not. And that is why it is overseen by a recloser, right? If there is a fault here, the recloser, if you look at this curve here, this is the time and this is the operating curve. The recloser has two operating curves, A and B, and the fuse has two curves, minimum melting and total clearing. Let's not get into a lot of that. That's the fuse, and those are the green ones are the recloser. So any fault that happens, which would be between these two values, we know that because we've done short circuit analysis, recloser operates first. So recloser operates, so the fault here is isolated, then it waits, and then it comes back and closes back again. If it closes back again, the fault is gone, you're good. If not, then depending sometimes on too fast operation, then it goes to the slow operation where it allows the fuse to blow. That means this scheme makes sure that the fault is permanent before the fuse is allowed to blow. This aspect, so recognizing whether the fault is permanent or temporary is an important function, okay? So if you can do that with some machine learning mechanism, that'd be a great contribution, okay? Because in this case, what happens is we still, we are waiting. So that is something that, and again, no, I have not seen papers that actually address this. There is also in transmission line, there is single pole reclosing, okay, which is employed. And there is a, so I probably shouldn't go into that due to the time constraints, but there's a problem of secondary arc. And before you reclose, you need to figure out whether the secondary arc is extinguished or not. The secondary arc is created because of the capacitance between the lines. Even when the recloser is open, there is a secondary arc going on. So, and then again, detection of secondary arc is a great application for machine learning based methods. Okay, so what's the bottom line? Bottom line is this, okay? It's a system. It's not one device, it's a system of devices which encapsulates the interdependent localized schemes, uses physical attributes of the power system to provide safety and stability, right? Replacing one or few elements will not reconcile with this holistic nature of the system protection, okay? Most every protection engineer looks for transparency. He or she has to know what's going on, okay? If you give them a black box, they will be very uncomfortable because you're talking of protecting very expensive equipment. Also, it's not perfect. Obviously, we know that it's not perfect, but its performance baseline is really high. As I said, the fault will be clear. So even if system fails, it fails in predictable and understandable and most importantly, correctable ways. You can predict if this doesn't happen, this has to happen. And if a series of operations happen, you know why they happened the way they happened. You can, in postmortem, you can figure out, okay, this didn't operate, there was a problem here, that is why we had this. That means you can correct it. So that's why transparency is essential for protection people, right? And again, failures are generally limited within certain error bounds. If you have say you guys are in Tempe, so you will never have a fault on a distribution feeder that would take out, the entire substation. Is very, very, very unlikely. So the damage or the outage is usually in almost all cases, limited to relatively smaller areas. So this is where we are. So, and you know, we will live here, we've lived here for years. Just imagine how many times we've lost power, considering that all our lines are overhead and exposed to weather, exposed to storms, right? Considering that, I think they're doing pretty well. Okay, so now let's look at what the papers do. So I've seen papers that say that, again, that takes just one scheme and then take their, do their testing, do their training, do that testing. Says 99.9% success rate of that one experiment that they perform. What you don't realize is if this scheme, suppose the utilities adopt this scheme, and they use that scheme in thousands of networks, what is going to happen is there will be daily dozens of non-operations in that system, even with 99.9%. So 99.9% is deceptive if it is employed on a very large scale, right? And of course, the lack of backup protection I already mentioned. So the consequences are dire. So, because if it doesn't operate, it's non-operation means something is going to blow up, right? As opposed to, say, image recognition. Well, it depends on where image recognition taking place. If you catch the wrong guy, you can, finally say, okay, my bad, and release that person. But in this case, but of course, if image recognition is going on in drone when it's attacking some enemy territory, then it becomes very important. But in protection, there is no such case as, okay, we can live with that. It's always going to create, either fire and then damage and a lot of outage, cost, everything. So that is why I understand that, because I've seen this, when I talk to people, they say that the protection people are very conservative. They are not ready to work with us, but understand where they are coming from. This is why they are conservative, okay? Okay, testing. Suppose you have field data. We'll see if you have field data on. Suppose you have field data. If you have field data that you collect at a substation, would it be useful if you are trying to train some device downstream? In other words, the data that you gather there downstream, the data that you gather at the substation, are they interchangeable? Can one data be used to train everything in the system? Think about that, okay? It is usually trained for that particular network. So if you use it in another network, or the network changes topology, right? It needs to relearn. The fault patterns are changed now, right? So is that okay? Can you afford that training time in the field? Can you do that? Can you wait? Also, people have done staged faults to gather the test data, but stage faults are few, and they are not really representative of all the faults that take place. An example is a high impedance fault. For example, of a lot of people have used AI, and it's a worthy method to use for this. But look at this high impedance fault, this high impedance fault, this high impedance fault. There's a tree burning here, and this is a concrete. This is basically just destroyed because of probably a 34 kV line or something like that has fallen, the live conductor falling. The fault signatures of both voltage and current. High impedance fault is where the current is so low that your usual methods fail. There's no overcurrent. But it's very dangerous because it's a live fault, and if you don't detect it, you're in trouble, right? So we have created theoretical models, and we use that, but people are saying, oh no, that's not, is not representative. But if you create staged faults, would it represent all this? Again, a question that needs to be examined. Data. Data is, and I think all of you know who have power, who work in power systems, that data is a problem. First of all, look at this bullet. So a lot of, now there are public domain PMU data, public domain system data, but we want actually fault data, right? What happens in the steady state, it's not of any use to us because the relays are operated during fault. How many faults, data sets for faults do you have? That is important, okay? So again, if you use different sensors, they'll have different resolutions. There'll be phasor, that could be time domain waveforms, there'll be harmonics, right? Even the same type of sensors will have different errors. You know, a CT could have variable error between plus and minus 10%. So understand that, okay? The more features you create, the more likely you need you know, data of different resolutions, diverse sensors, and then again, different sensors will all have different errors. The reason I'm mentioning this here is that the protection schemes that you see today, the legacy schemes, are okay with this errors. So the CT errors and the VT errors are encapsulated in their design, and they have been able to work around that. But when you do a machine learning based approach, remember that there are errors and you cannot assume you know, very, very accurate measurements. So that's another thing that you need to take care of. And then divergence. After all this, the faults are not well behaved, right? Each type of fault, even the same type of fault can have various, can vary from fault to fault. And again, if you simulated data, is usually very sanitized data, and a lot of faults happening out there will not exactly or even very closely match your simulated data, okay? And fault resistance is another unknown that will change everything. So again, all these, what we call covered balls, the protection systems today, legacy schemes, can deal with this. They have incorporated these aspects in the design, whereas for machine learning based systems, it's not yet shown, okay? So, and this is something you might, you know, relate to, for example, a self-driving car after all those, you know, 100,000 miles of whatever they did, and then they put it on the road and it killed somebody. So if there is something unexpected, the machine learning based techniques are very suspect to deal with it. So these are some of the things I thought that you should know, okay? So that when you design the schemes, you're aware of these pitfalls. So don't think that I'm kind of, you know, pessimistic about it. I'm just being realistic about these. Now, if you replace a physics-based relay with a data-driven relay, okay, which is what most papers do. They're saying, okay, here is my data-driven relay, testing, rather training, testing, we're done. Well, they are still using the same features. They're using current, voltage, frequency, rate of change of frequency. All these features or patterns, or, you know, combination of features, are already used by the relays based on the physics. So what is the guarantee that if you use the same patterns in a machine learning based or a data-driven relay, you will provide better performance? And I'm not saying you won't. I'm just saying you need to address this question. That here is, you know, the same patterns you're using. These patterns have been used for 100 years and fine-tuned and made to work. why will you give us better results with the same methods? Okay, will you be able to create better thresholds? Well, you have to consider this question. So now, if there is a pattern that has failed, if the pattern is not working, then if it doesn't work for physics-based relay, I would think that will not work for a data-driven relay as well. And this takes us to a more, what is going on in the industry today, in the power system distribution system today, with inverter-based relays or inverter-based resources. The overcurrent principle is failing. Why? Because look at this. This is where, so there is an inverter. Inverter typically limits its current. And the fault is taking place here. And after the fault, the currents are hardly increasing. So in this case, I've limited the currents to the same as load current. Typically, it's 1.1 or 1.2 per unit, which is not a fault level current. So if that means that the overcurrent principle has failed, right? So, well, if you use the overcurrent principle in data-driven relay, it is not likely to succeed, right? So the point I'm trying to make is, what is it that you're using in the data-driven approach that is superior to this? What features will you create? What inputs will you take? And the features that you create, you have to show that those features are performing better than just the interpretation of those features based on physics. I'm hoping I'm making myself clear here. So, solution. So yes, we agree that there is always need for or room for improvement. And in some scenarios, the machine learning techniques can provide better performance, augmented performance. But don't throw the baby with the bathwater. Okay, keep the baby there. So don't replace, in my opinion, okay, don't just just replace a machine learning, a physics-based method with a data-driven method. Okay, there's something that is going on and you guys know this more than I do. That's called a physics-aware solutions. That means you use the physics in your solutions, because I think the argument for this, I've seen that if it's just computation based, it becomes extremely expensive. But if you use physics in it, then it becomes more reasonable to compute. The computing part becomes easier. But in this case, actually the performance will get better if physics is, if you treat physics as a friend and use it in your solutions. Also, the other thing is, obviously there are applications that are not suitable to physics-based protection. For example, incipient fault. The fault has not happened, but it is about to. The insulator is getting worse, it's deteriorating. It's not failed yet, but it's deteriorating. Something like that, and the machine learning based methods would work wonderfully there because there's no physical model there, right? The other is, detect misoperations. As I said, misoperations are still not detectable in real time, which is very surprising and very frustrating, but that is the case, okay? Controlled islanding, for example. When there's a power swing going on, you don't want to just strip the relay that sees the power swing. You want to make sure that if there's a instability going on in a swing is getting unstable, the system should be separated at certain boundary so that the resulting separation, the two islands that are created by the separations, remain stable. All this is usually done offline through offline studies. And this is also called part of system integrated protection schemes, which are system-based, not local. And there, it is always set based on offline analysis. And if you can do it using real-time data and inform that system integrity protection schemes to operate in a certain way, if you adaptively change their settings based on the system condition, that'd be great. That's probably the holy grail, and I'm sure. So you know Vijay Vittal, right? He was saying the other day that we have still got to come up with a killer app using PMU data. And this is one of the killer apps. If you can do this, that would be great. Okay, so God, we got some time. Let me give you an example. So this is what we did when I was at New Mexico State University. We had an NSF-funded center there, which we called iCredits. And after 5 years working there, I still don't remember the whole full form of iCredits, but there is a full form there. And it essentially was given between computer science and electrical engineering department. The electrical engineering department, mostly power systems people, and the computer scientists were, you know, data scientists, communication experts, you name it. So, so this is something we did there. And I want to give that as an example because it will kind of show that even with an application that is worthy of machine learning, how many obstacles are you likely to get into, okay? So let's dive into this. So first of all, again, coming out to misoperations, if you look at blackout logs, right? So these are only a selected logs of blackouts that happened 96, 96, 2003 was the biggest one, right? All these blackouts, if you look at the log, you will see that something misoperated, some relay misoperated. The settings were not proper. The relay had a function, a problem that, you know, hidden problem that just surfaced at that time, but it misoperated. And what happens is, it's just so, just quickly going to the next slide. The Power System Relaying Committee actually made performed a survey some time ago. Here is the report. The yearly misoperations were 15%, 9%, 52%, 28% at 345 kV voltage levels for 4 different utilities that were surveyed. These are not small, right? But now every misoperation doesn't really result in a blackout, but these did. Okay, there you can actually see that some misoperation is responsible for either accelerating it or, you know, triggering it. So it's a serious business, right? And there is a phenomenon called load encroachment, which is common with all distance relays. So if you look at blackout logs of, I guarantee every blackout, you will see load encroachment, relay tripped on load encroachment. Essentially what happens is, quickly to give you an idea, if there are 2 parallel power lines, right? They are fully loaded, it's peak time, they're fully loaded, and one of them trips, right? So first of all, why would that trip? They are so much loaded that they become hot, they expand, and they typically sag into a tree. That happens, the line trips, and then the whole power is shifted on the other line, which for a distance relay, that looks like a fault. And the distance relay of that second line, which has no fault, trips, which means that it has, when you needed that line the most, it got tripped. And that is how the blackout progresses. So the load encroachment is very common for every blackout that, you know, that happens. So that's why so when I started working with PMU data, this is the first thing I realized that, okay, how about we track this? Because now we have PMU data. Can we use that to detect misoperations? So that's what we were trying to do. And this is something you guys know, Professor Meliopoulos at Georgia Tech. He's also trying to do that in a different way. He's not using AI, he's using dynamic state estimation. But it was interesting that two protection guys thought of the same thing about misoperations and started working on using PMU data for detecting misoperations. So of course, you guys are all aware how this works. There are PMUs and they feed to phasor data concentrator, and they're all synchronized because of the GPS, right? The older PMUs had, 30, even 10 frames per second. 60 is common now, 120 is pretty common, 240, if they're not there, they will be there. So 240 frames per second, that is a lot of data for our systems. Remember, the SCADA data is much less than this, first of all, in quantity, and it comes once every 2 to 4 seconds, once every 2 to 4 seconds. Now we are talking of 240 frames per second. That is why, can you hear me?
I can hear you.
Okay, good. I got a message saying your internet is unstable. I don't know. I'm in my.
Oh, okay.
Yeah, so I just wanted to make sure. So now, US has, at this point, I think 1700 until, what was it? October 2014. I don't know if I have the data before that, but after that, but it has slowed down. But there are quite a few PMUs here. In developing countries, for example, in India, it's a lot more aggressively, this is a lot more aggressively done, okay? They are installing PMUs like crazy. But this is what we have, right? And so how can we use this to detect misoperations? So here is the concept that we came up, okay? The data are coming from PMUs. And as you probably know, the data needs pre-processing. And we are not talking about pre-processing here. I'll just put a paper here, cited a paper here that we did based on, that was a part of another project, but that's, so suppose we did that, right? And now the pre-processed data comes in. And I think a lot of you who are working on PMU data have probably worked with disturbance detection and identification. What type of disturbance is this, right? That's a very popular application of PMU data. And we actually did it both using data-driven model, and then we used some physics-based model to inform our data-driven models. And we'll talk about that in the coming slides. Now, actually, what I'm interested in right now for my application is whether that's a fault or not. If it's a fault, and if the relay has also operated, so what it does is it sees if there is a relay that has operated, because when the relay operates, it provides a flag. And if the PMUs detect that there is a fault and the relay has already operated, we're good. It operated for the right reason. But if the PMUs don't detect a fault and you see a flag, then that's a misoperation, right? And then that misoperation, how to handle misoperation? Well, it depends. Typically, the operator knows, and then they take, they close the line back or something like that, or take care of the, disable the relay or replace the relay whenever possible. But at least there is a misoperation detection in real time. So that's what we were interested in. But since we were identifying fault, we also said we'll identify other disturbances as much as possible so that we have a supervisory layer for major events. If there is a dynamic event going on, generation loss, load loss, capacitor switching. So it's better, it's basically, we did that as well. So that's just goes to a visualization screen. So now, first of all, I don't know how many of you have actually got PMU data for disturbances. Again, remember I said that I don't care if you have loads and loads of PMU data for steady state or normal system. I want PMU data for disturbances, right? It is very, very hard to find. But we had a utility who were kind to us, and they said, here. So they had old PMUs, okay, 30 frames per second. They only had positive sequence. Now you have phase A, phase B, phase C. But they said, okay, you know what we do is we store all the PMUs. Basically, when they see there is a disturbance, they recognize it because rate of change of frequency or something like that will trigger that, and it stores that disturbance files separately. So they said, okay, you have for 4 PMU, for 4 years, we have all the disturbances that happen. We have them, okay? Now, so you can take them, all right? So how many did we get? 1,013 disturbances event files were we got, okay? Now, I said, okay, so we have quite a few known events, but well, they were just disturbance files. We didn't know what those disturbances were. So I sent a student to the utility, and he just went through the log of the utility, and you know how many log entries he found? 84 out of 1,013. So the ground truths that we really want for any application, only 84 events, 23 generation loss, 58 faults, and 3 line trips. Okay, so the majority of events, even if you get it, could be unknown, right? Which is really disappointing. So now, the rest of these events, what are those? We don't know, right? What are the exact number of classes that are residing in this data set? We don't know. So that's where we started, and we said, okay, so here is our strategy. First of all, how many, so we need to cluster these data, right? And figure out how many clusters these data can be segregated into, right? And then hopefully each cluster will represent one disturbance event, okay? And then we'll find out how many disturbance events are residing in this data set, okay? And then once we know how many classes we have, we use training and testing, because now we have how many classes we have, we know. So then you can form your classifier. So this was our strategy. And this is where, working with a data scientist was very helpful to me, because she was, she knew what to do. For this, the features that we used, and I'm not going to go into too much detail here. Most of you, if you have used, if you are working in this field, this is a very early work that came out of PNNL, where what they call minimum volume enclosing ellipsoid, MVEE. So they basically create an ellipsoid, and the dimension of the ellipsoid equal the number of PMUs. And the method looks more or less like a singular value decomposition method. But what we did was, if this was the file, this is where obviously the disturbance is. We took a window before, and then 3 windows during the disturbances. And for each window, so it's essentially what happens is it forms an ellipsoid. And then the shape of the ellipsoid is different based on different disturbances. So the geometric properties of the ellipsoid will be used as features. And so initially, since this was done already, it has shown good results. We use that. So we use that on voltage, we use that on frequency. So we create 102 features, and there were obviously 1,013 events. So each event was captured as 102 features. That was our feature matrix. And then we used an unsupervised clustering method, because this is what we do if we don't know how many classes are there. We used agglomerative hierarchical clustering. And when we did that, right, we got 19 groups, right? And these are the events that fell into each group. These are the total 1,013 events were divided into 19 groups, as you see here. Now, we looked at the known events, and the known events were, here was, the generation loss was spread across 4 groups. Fault was spread across 4 groups, and the line trip was just one group of all 3 events. Why is it spread across 4 groups? Where there could be a smaller generation loss, there could be larger generation loss. And what this method did was that it actually created different groups for smaller and larger generation loss. But the good thing is there was no misclassification. None of the fault event, which was known event, fell into the other group for generation loss, and vice versa. That gave us some confidence. Okay, this is working. So all we had to do is, make one single group of all 4, one single group of all 4. But then these are the ones that, so because of this, we said, okay, this is working. This is doing a good job. However, we don't know what these groups are. These are other events. These are not generation loss. These are not faults. These are not line trips. These are something else. So now what do you do? Again, so in this case, we then started look. So here is where the domain expertise comes in very handy for power. This is a power system problem, right? So we started looking at these, and we said, okay, this looks like a load switching on, load switching off. There were series capacitors in there. So that's what me and my students started looking at and said, this looks like this, okay? So let's say so now how do we confirm that it is like that? So fortunately, for the system that we were using, the 4 PMUs was in that southeastern system, and southwestern system, and that was already modeled on PSLF. So we actually bought PSLF license and those test cases, and we ran these events that we thought, load switching, capacitor switching, and all that. We ran those as simulation events, and then we added those events and ran the clustering algorithm again. And it actually gave us what we had assumed was correct. So finally, we came down to all the unknowns that you saw: load switching on off, series capacitor switching on off, pumping unit loss. These were synchronous motors, and that was typical for that system. They got lost. Then there was a generation loss. There's another 2 groups which were generation loss, and there was one remote fault. Sometimes what happens is fault takes place away from the PMUs. The PMUs still capture that, right? Same for generation loss. So then now if we put all these together, right, we have our classes. So fault, generation loss, switch on, switch off of load, series capacitor, line trip, and pumping station. These are the typical signatures. And if you look at this, these are faults. So voltage and frequency for fault, for generation loss, for load switch on, load switch off. It will, if you look at if you put your power system hat on, this is reasonable for this type of event. You would expect to see these. So that's how that was the first step to find out how many classes, okay? Now, let me show you a little bit of close-up here. The trigger was set as rate of change of frequency, and voltage. So if you see the fault signature here, suddenly the voltage goes down, suddenly the frequency jumps up and down, whereas in generation loss, it's pretty, placid. It's not doing anything that quick. So these are very clearly separated. Load switch on. Now load switch on, if you look at this, the frequency is doing what, a quick jump, but the voltage, not so much. Same here, right? Synchronous motor, again, very different signature. And then this, we didn't actually have a field data, so we created this data for capacitor in and out. So this tells you that if you can actually see, so this is where, again, the domain expertise of my computer science colleague came in handy. She looked at this and she said, you know what, the features are, the raw data has a lot of information here. So instead of using any domain transform, why not we use just the raw data or a method based on raw data? And that should do it. So she had started working on shapelets, and that's what she did. So in the interest of time, there was noise. So if you look at the data, and you know that anybody who has used PMU data, it always has noise. And this noise is not easy to filter. You cannot design an FIR filter for this. So we kept the noise as it is. And we also studied the noise in all LV, MV, and EHV measurements that we had from other projects. It's about 45 dB. Okay, we kept it. Data-driven approach. So what pattern works the best, and then what classifier works the best. So again, if you wanted to build a classifier, you need ground truths. You had 23 generation loss, 58 watts, and 3 line trips. Those were your ground truths. That is not enough. So now we simulated, again, the same PSLF model. We simulated more faults, more generation loss. So we actually simulated a bunch of disturbances to include. Now, since there were multiple people involved there, so we said, okay, let's do domain transform also. Fourier, wavelet. There was a postdoc who was a big fan of S transform, which is basically a mother wavelet is replaced by a Gaussian windows, and there's a phase term there. PCA, Hilbert, so you name it, like these are all heavyweights. Then we said, okay, raw data. We just do the slope of raw data, statistical based features, and then shapelet. So shapelet is basically a subsequence so what it does is it creates a subsequence of the time domain data. And how it does that, we'll probably skip that because we're kind of getting near the 1.25 hour mark here. But usually the shapelets are good, but they are very computationally expensive because for a time series of length n, the subsequences to be tested are n times n plus 1 over 2. So if we had a 3-minute window, but we shortened it to a 2-second window because that's where the disturbance signature was seen the most prominent. So because of that, we called it domain-specific shapelets or D-shapelet, and that worked. So that reduced the computation burden a lot. And we also created another feature that was the slope sequence of shapelets, which basically took a slope across every point of the shapelet. And then we tested. We had done some tests before, and the KNN and support vector were quite promising in that study, which is in this paper. So we did that. Okay, let's look at the results. So what we did was all simulated faults and generation loss were used for training, and the field data was used for testing. Then here, all 7 disturbances, simulated disturbances, were used for training, but for testing was done only for fault and generation loss. Look at how these perform. All these heavyweights are not really doing very well. So we took voltage and also voltage and frequency both. Voltage and frequency both is better, but if you look at raw data is 93, 95%. It's even better than some of the transforms. But the slope of shapelets, which is S cube, performs the best. Here also it performs the best, right? Okay, so this was simulated data for for training, field data for testing. Then we took all simulated. So 90% of the simulated fault and generation loss, and then 10% of that was used for testing. We did 10-fold cross validation. That means all the data that were used for training once was also used for testing 10 different times, right? And now you can see that because this is simulated data and it doesn't have noise, these methods start performing much better. These still perform well, but the other ones, they perform better than before. Here, we are doing all simulated 7 events, and then we are testing it for 7 classes, not just for fault and generation loss, all 7. This is where the performance falls the most. If you can see here, the methods that are giving almost 100%, 99% performance drops to about 88%, and the best is here 91%. Why is this happening? Well, we looked at this and we saw that all the problems, all the misclassifications were happening in load switching off and generation switching on, or rather generation switching off and load switching on. So if you look at the physics, they exactly have the same physics, right? System loses the load or gains the generation. It's the same effect, and vice versa is also the same effect. So load on and generation loss were the main sources of error. And that is why, this is why it shows that, you know, now if you use some physics-based approach to this to help this out, this can get better. And that's what we did. I'll give you like 2 or 3 or 4 minutes. So it took about 0.4 milliseconds, of course, for all this to happen, which is fine. For you know, misoperations, you have more time. And the fault classification was perfect. Okay, even with for any of these cases, the fault classification was perfect. That's what we want for misoperations. So that is a good news for what we call supervisory protection. And then another CPS, the NSF grant that we got was essentially using a physics-based approach. We used energy functions. Now, energy function, typically, they've been used for a long time. Okay, you'll see papers on energy functions, the 70s. But it is a big, humongous function that captures all the energies of a power system. What we did was, so that energy comes from generation, comes from load, comes from line. So this is what, you know, this comes from these two, W22 and 23 are representing loads. 25 represents the line energy. 21 represents the potential energy in the generator. These are the components of energy function. So we said that if there is a fault, I would say the line energy function would be impacted the most. If the load changes, this is going to be impacted. If the generation changes, this is going to be impacted. So the problem we had between the generation and the load, we resolved by using components of energy function. And our assumption was correct. If you look at this, the generation mechanical input changes. So this 2-1 changes the most for generation. But if you look at change in the load, you hardly see that changing. The load component, the load energy function is changing perceptibly here. So that problem between the generation loss and load, generation and load events was resolved using physical attributes of the system. So I guess in the interest of time, I think it's all that I needed to say. We could have gone into a little bit of detail of this, but that's okay. You got all the papers there in case you're interested. So at the end, physics aware AI solutions. So make, AI and physics, if they are friends with each other, we can go a long way. There are some problems that the protection engineers have not been able to deal with efficiently, where AI can be helpful, right? And then the example essentially showed how much of how difficult it is to first get the data, disturbance data. If you get it, using it it's challenging, right? Now we wanted to take these results and validate it with another set of data from another set of PMUs. Nobody gave us that data. Okay, all my friends at different utilities, different ISOs, they were all okay with it. But when it got to the lawyers, they killed it. We never got more data to validate this further. So this just gives you an idea that it is very hard to get field data for disturbances and for faults. So with this, I will, so there's an article that we wrote in Electrification magazine, the March issue, that talks about some of these. And this second paper talks about the example. So with that, I thank you very much for your patience and for your listening and for your attendance, and we'll take questions.